And greetings. Welcome to the Evidence and Reasons for the Christian Faith video channel. I'm Salvador Cordova, and I'm joined here. I'm privileged to have my guest, Jordan, and we'll be talking about, this is going to be a nerd torture session. We're going to be talking about nuclear physics and radiometric dating. Just as an introduction to the channel, we cover evidence and reasons for the Christian faith. The audience tends to be Christian graduate students in the sciences, particularly biology, but also other fields like chemistry. There are not really many physics students, although I'd love to meet them. So that's kind of like a rarefied field.
Good. Nobody will check my work.
Yeah. So a lot of people might be surprised to hear that, really my background's physics, not biology. I was an engineer in the aerospace and defense industry. I have 5 degrees. One of them is in biology, but the other 4 are really physics and engineering related. So I'm looking forward to the show. I'm an evangelical Christian. I profess kind of the somewhat reformed interpretation of the scriptures. I'm a young earth, young cosmos creationist, but just for those who are curious, I was an evolutionist at one time. I became a Christian and stayed an evolutionist for about 1 or 2 years, then became an old earth creationist, and eventually a young earth creationist. So that's been about a 40-year journey for me. I worked professionally for a famous secular scientist who also became a young earth creationist, John C. Sanford. I worked for him for 7 years. I still work with him, but no longer as his paid employee. We're hoping to publish some more papers this year. We were privileged to publish in a secular venue last year, although he's a very accomplished secular scientist. He was a retired research professor at Cornell, and also his invention, the gene gun, is in the Smithsonian National Museum of American History. So tonight's topic is radiometric dating. I would classify, there are many problems with the young Earth creation model from a scientific, observational, experimental standpoint, etc. I'm one of the few young Earth creationists who will say there are major problems there. So people might ask, well, why am I a young Earth creationist? It's because I think the other side has worse problems, honestly. But we're not here to debate, and I didn't mean to offend any of the people there that have a different viewpoint. I just tell it the way I'm just expressing my opinion, and I try to be courteous to most of my guests here. There are people that visit the channel and I don't like them and I toss them. So it's not like I'm nice to everyone. So if I'm really nice to someone, that means that I think they're really great people. Just so you know there, Jordan. And let's see what else to say. So I think it's really important that we hear from the other side. When I was studying, when I was working for Dr. Sanford for 7 years, out of his own pocket, he sent me to the National Institutes of Health, FAES graduate school, to learn about God's creation under evolutionists and even top evolutionary biologists. And that is something that, and I went to graduate school in applied physics at Johns Hopkins, and I think all of them were old Earth people and probably evolutionists. Now, the funny thing is I found out there was another young Earth creationist in the physics program, and we were laughing because the professor would sometimes tell jokes against young Earth creationists, and we would just laugh along with him. It was so funny. But anyway, Dustin, it's great to see you. And oh my goodness, Dr. Dan is here, and Dave. Hey, your fan club's here, Jordan. So a lot of my audience are Christians. So perhaps you could explain a little bit about, what you think might be valuable for them to know about you, and then we'll just get to the topic.
Sure. My name is Jordan. I am a nuclear and mechanical engineer. So I have a bachelor's degree. I haven't been to graduate school yet. I got that a few years ago from VCU. I used to be a Christian. I used to be a young Earth creationist, actually. And my journey is kind of almost the mirror of yours. I'm an atheist now, but what's most important to me is the evidence, and I want to hold true beliefs and not false beliefs. So I changed my mind in the past. I'm happy to change my mind again if the evidence persuades me.
Well, that's fabulous. As much as I and probably others are very curious about your journey, that's not why I I invited you here today. Maybe that's a conversation some other place when you feel, if that's something of interest to you. But um, I have to say that where do you and I agree? Um, I actually thought uh, the young Earth creationists have been giving uh, they keep advocating for accelerated nuclear decay. And I felt your criticisms of that were spot on. Now, I have to
Yeah.
qualify that. There's there are multiple accelerated decay models. And one of them is what I call the isotropic decay model, where all across the universe, for some unknown reason and no reason in particular, uh, nuclear processes just started going real fast. And I think that is very problematic. You can't prove it. That looks very ad hoc. And um,
I mean, it
so
also would cause the Earth to melt, which is an
melt.
issue.
Okay.
Yeah.
All right. So I think, uh, I've had discussions with the other side, and I think whenever they put problems, it's irresponsible to sweep it under the rug. Especially, okay, you might, sorry to take a swipe at Kent Hovind again, but a fast talking salesman like that, if he has an unsophisticated audience, he can get away with stuff. But a lot of my audience are science students. All right. You don't, they will be going to secular schools. They will be dealing with this at some point. I feel a responsibility to, at least warn them. I said, okay, I got a level with you. You know, um, I came from an evolutionary background. I think the Earth is young, but if you sign up for that, you're going to face some problems. The option is to say, I don't know, and I'm undecided. But I think because young Earth creationism has a lot of religious implications for a lot of people, they're willing to say, okay, I'm going to accept it on faith rather than just wait. So there are real questions out there that I could care less about. And it doesn't impact kind of the way I live my life. Um, I mean, there's some questions about like string theory. I could care less. It doesn't have a bearing on my, how I live my life or the decisions, kind of the faith I adopt and so on and so forth. But the young Earth creationism is one that does tend to imply kind of a demand on your lifestyle. So, um, like I said last night, there are three options. You could say, I believe it, I don't believe it, or I'll wait. So for the young Earth creationists that out there that are matriculating through school, for a lot of them, it's like they will have to take it on a step of faith. It's not totally fact-based. And because it's not, they will encounter data points that are uncomfortable. And they need to know how to deal with it. And it's my responsibility to communicate that. And sometimes it's kind of hard to say this, but sometimes some young Earth creationists are so wedded to their model that when you criticize them, they make it like you're criticizing young Earth creationism. It's like, well, no, I think maybe your physics is wrong.
Yeah.
Maybe you need to look for another solution that'll actually work. So,
Right. And like I post all of my calculations whenever I do a debate or something online because I want to be corrected. If I'm wrong, I want to know, and if someone is able to point out a place where I made a mistake, I don't take that as a personal attack. It means I'm wrong and then I can change and then I don't have to be wrong anymore. So, I mean, it
right.
helps me.
Exactly. I mean, it's kind of scary just from the emails I get. People are looking up to me to answer the questions correctly. And I'm just like, what if I screw up and I give them a data point and they go to their professor and they get dog points? That would really bother me. And so that's why I've been grateful for people like you and Dr. Dan. Just like I said, okay, Dr. Dan, you're a professor of biology. Is this okay to teach? And even if
So
I Go on.
I was about to say, I have to say that when I'm talking about something like tonight, I'm actually more nervous than when I talk about like things that are not in my field. Because if I make a mistake over there, well, I'm not a biologist. It's fine. But if I make a mistake about something basic here, it's always my fear that I'm going to completely screw it up. You know, a bit of imposter syndrome.
Okay, so I think what would be, I try to look at the comments here, so I kind of gauge what the audience is. I entitled this "Nerd Torture," guys. This may, unless you're an ultra nerd or a masochist, I don't know how you could keep your attention level. But
Well, I think nuclear physics is really cool. So
okay, all right. So now, why don't we just? Okay, so you're a nuclear and mechanical I didn't know you had also mechanical engineering. So
yeah.
all right, why don't we compare notes as far as what we learned in school? I had to learn kind of the basic math, the calculus, differential equations, linear, matrix algebra, linear algebra. How about chemistry? Did you have any chemistry classes?
Only the gen ed chemistry that everybody takes.
Okay. Did you have thermodynamics? I had.
Yep.
Okay. I could see we're going to be on the same page on a lot of things.
You
probably had 3 semesters of physics, because that's standard for most.
I had 2 or 3. I had 2 required, and then I got a minor in physics, so I took another semester after that.
Wow! So you have a bachelor's in nuclear engineering and mechanical engineering with a minor in physics.
Yep. Which the minor is actually really easy to get because a lot of the nuclear related courses they count for physics courses, so it was not a big jump. It just had to go take a minor in physics class.
Okay, this is going to be a great discussion then, because you and I are on the same page. We've suffered through the same coursework.
Fluid mechanics, heat transfer, mechanics of materials,
Okay, I didn't have fluid mechanics. I didn't have heat transfer. I did have lots of. I've had 2 classes on thermodynamics. I had classical. Did you have statics and dynamics?
Statics, dynamics. It goes statics, dynamics, then mechanics of materials, and then that you build off of those when you do your thermal system design and you do your PSD and etc.
Okay, guys. I'm trying to tell the creationists out there, this is what you'll be in for if you go to a science school. And you have to be able to articulate your case to audiences like this, to really move the needle, so to speak. And I had solid state physics. I didn't really have mechanics. And actually, I think I did. And it's really bad because that might have been 30 years ago that I had a little bit of mechanics of materials.
Mine was only like 3 to 6 years ago, so it's a little bit more fresh, but still, a while.
Did you have to study deformables?
That's mechanical materials.
Okay, then that part I didn't have.
Deformables is like another word for it.
Okay, no, come to think of it, I don't think I had. I wanted to study mechanics of materials. So as a physics student, this may surprise people. The schools I went to didn't have any nuclear stuff. So it's kind of embarrassing when I hear people talk about nuclear structure, and it's just like, so this is, I've had to kind of pick it up on the side. I mean, obviously, there's some basics in nuclear structures, like you have a nucleus and you have the electrons.
Yeah.
Okay, so but there's some finer points that are relevant to this discussion. I'm just like, okay, I might have to be spoon-fed here, and I'm sorry that if I have to impose on you to walk me through some of this.
As an engineer, I did, learn some nuclear physics, but I'm definitely not a physicist. So there's a level of physics past which I just hit the I believe button, and just I can apply it to a nuclear reactor,
Okay, so what I'm gonna and feel free to do this, Jordan, if you want to do like a share screen or anything. I was thinking we could just go through kind of the Wikipedia pages.
Sure.
Just to kind of talk.
I did notice a question in the chat I don't know if you want to like save those to the end, or if you
Oh,
want
go
the answer
ahead.
to come in,
I,
or whatever.
it just, by the way, guys, I usually don't, I have a hard time reading the chat while I'm talking and interacting, and I probably missed 75% of what's there. So, but go ahead, Jordan. What did you see?
Dustin Buck asked, "Does mass get lost after radiation from the isotope?" So that's a great question, and that's going to tie into some of the stuff with radiometric dating and the mass defect paper that might come up later. But so the answer is it depends on the isotope, but so mass energy isn't lost per se, because mass can't be created or destroyed, and mass and energy are equivalent, right? So they can be changed into each other. So if you total up all of the energy of the system, the isotope before and after it decays, all of that energy is conserved. So the kind of glib answer would be no, because it has to go somewhere. But you can change forms, right? So when hydrogen fuses, if you get two hydrogen atoms and they fuse into a helium atom, if you measured the mass of the hydrogen atoms before and the helium afterwards, the helium atom would weigh less than the sum of the masses of the hydrogen, right? So there's less mass now than there was before. Now, I just told you it has to be conserved, so where did it go? It went away. It gets released as energy. That's how the sun produces its energy. There's the nucleons, the protons, the neutrons, have an energy that it requires to hold them together, and it's less for helium than it is for hydrogen. Hydrogen doesn't have; it's just a proton. But anyway, regardless, so that's what it's called, a mass defect. So to answer your question, yes, mass can be lost as energy after radiation or after fusion or fission or any kind of nuclear reaction.
Okay,
Hope
so
that answers the question.
yes, and we'll revisit some of this. This question, since we can now accelerate radioactive decay, does that make radiometric dating possibly an error? Does the magnetic field strength affect radio decay? We're not going to answer that right now, because actually the whole show is kind of building toward relating to this. So I know a lot of people probably signed up to see the punchline here, a simple yes or no. And I would say it depends. It depends on who you ask, and maybe some things are not completely resolved. Just that Mark has been a long time visitor here. Just to say here, I would just say, even as a young Earth creationist, I'm cautiously optimistic, but that's not, I wouldn't be out there and be as emphatic about accelerated nuclear decays in a local context, like in isolated context, as I'm emphatic about that I think abiogenesis required a miracle. So also, with respect to accelerated radioactive decay, Mark, if you were coming late and you missed it, I already said that I agree with Jordan that this universal accelerated decay is probably not a good avenue for young Earth creationists. I think I would agree that you'd risk incinerating the Earth, but there are also other problems, and I pointed this out at creation conferences. If you start tampering with the weak and strong force, you have to account for why the sun doesn't blow up, or something equally catastrophic. It's like, okay, I've been saying this is territory you don't want to go.
Once you start tinkering with fundamental physics, weird things are going to happen.
Yeah. Or messing with Planck's constant. I'm just like, okay, so kind of the short answer is there are more than one accelerated decay models. But maybe just looking forward a little bit, because I had an earlier show where I was talking about photonuclear processes. I mean, I just found some stuff. My understanding is that there's attempts to use high energy photons in the gamma rays to accelerate certain fissile products of fission in the reactors. I mean, waste products.
Okay.
Have you heard of that? Was that taught in your classes, or have you encountered that at all?
So you're asking if you can use high energy photons to speed up or to transmute
Yeah,
things?
transmute's a better word. I only
Um,
saw a report of that like in the last. I've only heard, there was a Nature report 2022. So if you that may give me a feel for how recent all this is.
so there's discussion about transmuting radioactive decay products, particularly as it pertains to nuclear energy. Usually, it's not photons that would do it, but you'd bombard it with neutrons or maybe protons to if it absorbed a neutron, it would become a different isotope, right? So, or the same thing, if it absorbed a proton, it might become a different element. So, um, there's talk about doing that to change maybe some of the transuranics, which are elements that are heavier than uranium, or any of the products to a form that's either stable or maybe one that decays faster. So it would be more radioactive in the short term, but it would be safer and maybe easier to contain. Um, so that is something that's been looked into. I'm not aware of any like cost effective method. And in terms of like a gamma ray doing it, uh, I mean that wouldn't transmute because the gamma ray doesn't. It's a photon, right? So, but it's possible you could excite it and cause it to be more unstable and like maybe prefer one decay path over another because the energy of the system has to do with that. That can play into which decay path it takes. So.
Okay, so this is just like this year, this one here.
Mhm.
I mean, I've sort of heard it, and I'm just going to briefly run through it. And this is, I'm not trying to put you on the spot here, Jordan. I only found this like last night, and so Mark, uh, this is just to whet some people's appetite. So this is in Nature Scientific Reports, and I'll try to put the link in the video description after we're done. And it talks about, why don't I just read the abstract here? Because if I try to summarize it, I'm going to totally mess it up. So I'll just read the abstract here. Disposal of long-lived fission products, LLFPSs, produced in reactors has been paid a lot attention for sustainable and clean nuclear energy. Although a few transmutation means have been proposed to address this issue, there are still scientific and/or engineering challenges to efficient transmutation of LLFPs. In this study, we proposed a novel concept of nuclear energy system, advanced nuclear energy system for transmuting LLFPs efficiently without isotopic separation. You can see these are Chinese speakers, so the English could be a little bit wobbly here. So I want to grant them a little charity here. The ANES comprises intense photo neutron source and subcritical reactor, which consists of lead bismuth layer, beryllium layer, and fuel, LLFPs, and shield assemblies. The PNS is produced by bombarding radioactive cesium and iodine target with laser Compton scattering gamma ray beam. We investigate the effect of ANS layout on transmutation efficiency by Monte Carlo simulations. It is found that a proper combination of lead bismuth layer and beryllium layer can increase the utilization efficiency of the PNS by a factor of 10, which helps decrease almost the same factor the LCS gamma beam intensity required for driving the ANES. And way down here, I'm just going to, since this wasn't the main focus, just to kind of keep the interest to where this was possibly headed, I was interested in this. Let me see if it says, I'm going to look for half-life. While I'm searching for this, if you have any
Okay.
comments.
So I've not read this paper. It's the first time I've seen it. But my guess is what they're doing is they're not transmuting something directly with the gamma rays, but they said that they're using it as a photoneutron source. So they'd be basically dislodging neutrons and then they'd be absorbed in the target material. and that would be what would be doing the transmutation, which makes a lot more sense to me just offhand. Because you're talking about transmutation, it's usually going to be a neutron or a proton that you're absorbing.
Okay, yeah, that was very, very helpful, by the way, because at first I didn't pick that up until you just said about using the neutron to do a transmutation.
Right.
So I stand corrected about using gamma rays directly. I seem to have recalled someone mentioning that before, and I may have misremembered. So thank you for.
So yeah, so what that would tell me is, so if you change the half-life in that way, you aren't changing the half-life in the sense that like the decay is happening at a faster rate. You are changing it in the sense that because it's absorbing a neutron, so it's going to decay in a different way than it would without those neutrons, that other way might be faster. So its effective half-life would be faster. So that is a little nuanced, but basically if you imagine it has a half-life of, say, I don't know, 10,000 years, and it's decays by alpha decay, so it emits an alpha particle. Imagine that. But if you can get it to absorb a neutron and it fissions, and it does that with a half-life of 50 years, its effective half-life is much shorter now, but you didn't increase the half-life of the alpha decay, if that makes sense.
Yes, okay. That was actually okay, so here is the sentence that stood out. T effective can thus be reduced from almost 10 to the 6th years to a level of 100 years. Okay, so you've actually, you saved me from making a really bad error, by the way, just now.
You're welcome. Yeah, T effective, so that tells you there. It's the effective half-life.
Yeah, so, but I did not know that gamma rays could just kind of going on this topic, this they call it disintegration. Photodisintegration.
I mean, if you think about it, a gamma ray is a super high energy photon, right? And so just kind of going to billiard ball physics, if you imagine the nucleus is just like a clump of protons and neutrons, and this gamma ray blast comes and hits it, it could dislodge some of the nucleons. That's not physically what's happening, because, you know, they're not actually like a bunch of billiard balls, but, you know, for a dumb engineer, that's good enough, you know, for me.
Yeah. Okay, so the thumbnail had this it was actually a photo disintegration here.
Yeah.
So it's if you don't mind, I'll just read it for the sake of everyone here. Hang on, that's the wrong. Hang on, I had the wrong. Photodisintegration, also called phototransmutation or a photonuclear reaction, is a nuclear process in which an atomic nucleus absorbs a high-energy gamma ray, enters an excited state, and immediately decays by emitting a subatomic particle. The incoming gamma ray effectively knocks one or more neutrons, protons, or an alpha particle out of the nucleus. The reactions are called gamma N, gamma P, gamma alpha. Okay, so that's I mean, just this may if people are wondering why I threw this out there, this is a lot of what research is about. Sometimes we'll go down something and it's a total rabbit trail, but I found that you have to do that because sometimes you get you might get a data point that's useful in the future. So
quick question in the chat. Godzilla Freak asks, would appeared half-life be an appropriate description? Maybe. I think effective half-life is more apt, because that's what it means. Like, it's not that the half-life appears different, it's that it's effectively different. You're going to have less of the stuff faster, not because you've changed what was happening before. It's just decaying in a different way. But I guess you could say appeared.
So just for the viewers' benefit, I kind of heard about these kind of interactions in passing. And it's only like last night, because in preparation for this show, I was just Googling around and just like, the idea of being able to transmute to actually affect nuclear structure with gamma rays is, I'll tell you why this is interesting. I'd always thought, okay, you can't do molecular alchemy without fission or fusion or hitting it with particles like neutrons. So I'm finding all these ways to change the nucleus.
Mm-hmm.
And I'm just throwing that out there for the young Earth creationists. It's like, this is a little bit more subtle. And then there's the whole thing about cold fusion. I think some of the reactions may not be fusion at all. There's so many ways to, we're getting transmutation reactions, but Jordan, please go ahead, say what's on your heart, brother.
We can't do hot fusion. Let's figure out hot fusion first. I don't know. Cold fusion seems like pixie dust to me. I'm extremely skeptical that that's going to happen.
All right. So I mean, I don't mean to frustrate the readers because you're just like, well, what's your point, Sal? And it's like, no, this is a nerd torture session. There may not be a point. We might just have to look at the data. This is like kind of a fishing expedition, guys. And as a professional researcher, I've been on a lot of fishing expeditions and come up empty. So I'm taking you along the way, but it's also a learning opportunity.
Do you want me to keep answering questions from the chat? I don't want to cut you off in the middle of a point.
Oh, why don't you answer one question and then I'll get to my graduate term paper.
Okay, cool.
And how we got the topic.
Man, there's so many questions. Okay, so go in the order they were received. Mitchell asked, concerning thermodynamics and the EVO's Big Bang, how did water itself gravitate to Earth without Earth-ending bombardments of comets, causing a heat problem exponential to your model of big years? So I've heard this before, that the comets, when a comet slams into the Earth, an ice comet or something, that's a lot of kinetic energy, that's going to release heat, and that's going to cause a heat problem for the old Earth model. What you have to remember, though, is the time involved. So the reason there's a heat problem in young Earth creationism, I forget the term you use, but if all radioactive processes were uniformly accelerated.
I use the word isotropic. I don't know if that's even the right. Universal. I don't know why they use the word isotropic.
Isotropic makes sense to me. But, isotropic, universal, whatever. The reason that's a problem is because they try to smash 4 billion years worth of decay into a year, right? If that amount of heat that's released over 4 billion years is not a problem, if you release it over 4 billion years, it's trying to condense it all to 1 year. That's the problem, or 6,000 years. So same sort of thing with the comets. If the comet's delivering this ice to the Earth, they don't all show up on one day and mass bombard the Earth, it's happening over billions of years. And also, Earth was like a molten ball of fire when it first started, so like, it's just not a problem because of you don't have to, the temperature can go high because you don't have to be in a situation where a wooden boat has to survive. And it also is happening over billions of years. So,
well, Leo Phileas is here. Greetings, Leo. I actually wrote Leo Phileas because one reason, now that I know you're a mechanical engineer, Jordan, we can have some really nice talks. I mean, angular momentum is something that you had dealt with for sure, and your statics and dynamics class. Mm-hmm. Just I'm sorry to do a little advertisement here. This is a commercial break. One reason I became a young Earth creationist is I read this book, Solar System Evolution, New Perspectives. Now, this is a 30-year-old book, but some of the problems they highlight are still there. One of the major problems is the angular momentum problem. And it's not clear, like a lot of physics peer-reviewed papers, it's, unless you're a specialist in the area, it's easy to miss what their point is. But suffice to say, it's a known problem, but it's not always articulated in a way that I could re-articulate it. So I did invite Leo Phileas to talk about angular momentum. The problem is, it's like when you have a figure skater and their arms are extended, their legs, and they're spinning. When they pull in, there's conservation of angular momentum. They have to spin faster. Now, the supposed solar nebular disk would have comparable angular momentum problems but it's a little bit more difficult because you're not connected, and you have gravity there, you have potential energy, and the orbital mechanics start to get kind of nasty. It's not so bad when you have like one big body and one little tiny satellite, but when you have all these particles and in-body problems, just nightmarish. But the way I understand it, the sun should be rotating much faster. And this is an unsolved problem, and that's why I wanted to explore it. That was the thing that triggered my interest in young Earth creationism, because it was shortly after I took classical mechanics and just like, man, I don't know how to deal with this problem. So Leo does just a little advertisement on what I do want to cover on my channel at some point. So why don't you take another question, and then I'll go to my graduate term paper.
Sure, I've been nailing a couple of the easy ones, but let me. X-rays.
Oh, by the way, I concur with your answer. By the way, if I disagree, I'll say so. So if if I'm generally side, the default is I agree with Jordan.
Would this effective decay? Sorry, it's jumping around on me. Would this effective decay have a difference in resulting appearance in comparison to alpha decay? I think what that's Wesley Coleman. I think what Wesley's asking is if the thing you'd get at the other end, the results, the daughter products would be different, and yeah, they certainly could be different because you're taking a different decay pathway. So the composition of stuff you'd get at the end could vary. I would say would likely and almost definitely be different.
Okay. So this is, to me, when I read all these things about photo-induced nuclear reactions, it was heartening. But I'm just like, okay, we still got a huge hill to climb over. If you're a young Earth creationist, to be able to connect the dots to come up with a coherent theory. But anytime that I could see other mechanisms for affecting nuclear structure, I get a little heartened. So now this leads to, again, my journey from old Earth to young Earth creationism. I began to have doubts about solar system evolution, definitely dismissed abiogenesis. And if you want to see the reasons why, I think James Tour can articulate it better than I can. I began to look at this book, Solar System Evolution, and I got convinced the solar system was created. My professors at my university were rejecting the Big Bang, 3 of them openly and 1 kind of quietly, and he was my professor of supplemental quantum mechanics, Dr. James Trefil, who's a famous science teacher. So it was in the secular schools that the doubt started to be happening upon me, and that was kind of my transformation from old Earth to young Earth. And so one of the questions that came up is, what about, when they say radiometric dating, there are so many different decay isotopes and pathways. It's like, it's very hard to make a generalization. You can't apply, if you find something like, something that uses one form of decay, you can't generalize it to another form of decay. And it ends up, we have a lot of special cases we have to deal with. But that being said, in my graduate classes, we're all kind of equal in ability. So it wouldn't be unusual for me to be at the top of the class and in one class and at the bottom of the class in another with the same group of guys. I was at the bottom of my solid state physics class, and the professor said, well, just, for a term paper, that's going to be a big part of your grade. Just, pick a topic related to solid state physics or condensed matter physics. And I said, I got to save my grade here. I don't want to get a C. I want to get at least a B. And so what happened was I said, okay, I'm going to look at all the ways that we can affect nuclear structure with chemical and electrical means. And I said, either he'll flunk me or he'll love me. And so I went to the university library. Said, I'm not going to cite creationist sources, obviously. I'm going to cite mainstream sources. I'm certainly not going to go to the internet and just grab random stuff. I needed to, you expect me to be a scholar here. I was actually shocked my jaw dropped at how many things that, I thought I knew, or that I was taught about changing nuclear structure. It's way more subtle. It's way more subtle. Like at the time, had I known about photo disintegration, I would have put it in that. So what were some of the things that I found? And, correct me if I'm wrong here. There is, this thing about cold and hot fusion. It's almost kind of a misnomer as far as I'm concerned. It's talking about how you reduce the Coulomb forces between, like say if you're having, two positive, what do you call the center of the nuclei? Two positive nuclei coming together. If they're both positively charged, you have to overcome the repulsion. We call that the Coulomb force. And so one of the mechanisms is just to heat it up so much and they're colliding, and some of the nuclei have enough energy to get close enough to overcome, and then the other nuclear forces take over. Did I describe that halfway right? Can you describe the process?
That's right. It's they call it overcoming the Coulomb barrier. There's like you said, like particles repel, just like when you try to mash two magnets together. If it's the same pole, they're going to repel each other, right? And the closer you have them together, the harder they're going to repel each other, right? If you smash them together hard enough, if you get past the hump of that intense repulsion from the electromagnetic force, then the other forces take over, the nuclear forces take over and bunch it all together, right? The reason that the nucleus holds together, the nucleus is a bunch of protons. They're all positively charged. So the electromagnetic charge between them would want to have the nucleus explode. The reason it doesn't is because there's other forces that are stronger. The strong nuclear force is stronger but shorter distance, right? And so you have to overcome that barrier. Okay. But that's a generic case. There's more to it than that, like because quantum mechanics is a thing, you don't necessarily have to climb over a barrier. Sometimes you can tunnel right through it.
Tunnel through it.
But that's like the generic case.
Okay, so one way to overcome that, and I just threw this in. This was in my term paper. I said muon-catalyzed fusion. It's a process that takes place at temperatures significantly lower than the temperatures required for thermonuclear fusion. Even at room temperature or lower, it is one of the few known ways of catalyzing nuclear fusion reactions. Have you heard of that one, Jordan?
No, I got to be honest. My engineering degree was focused on fission because that's how we produce power. So we did talk about fusion, but it wasn't.
I suspected you'd be the fission expert here.
It wasn't a focus because, well, fission's just 20 years away and always will be. So.
So, I saw here that they were able to accomplish this fusion below freezing temperatures. So I think the reason I threw this out for we were supposed to give presentations to the class. I said I at least had to throw the muon-catalyzed fusion because I knew I was going to start to talk into territory that was kind of like cold fusion. And I just wanted to establish the fact we can do the fusion reaction at low temperatures. But it's very hard to get muon, so this may not be a way to make fusion, okay? But I thought this was really cool, and I just lucked out that there happened to be this muon-catalyzed fusion. So, so that was one part of my talk, and like I said, given that Hopkins isn't a nuclear school, I'm sure all the students were like, "Wow, that's kind of cool." So, what was the other thing that was in my term paper? Well, I said, well, lightning can generate neutrons. It was a 1984, 1987 paper in Nature. I found that was interesting. You can use electricity to generate neutrons. Now we actually have a better measurement that was done in 2017, and I may read that. But of interest to the young Earth creationists, and I'll tell why this is relevant. There is an anomaly that we creationists cite is the fact that there's 70 times more uranium on the continental crust than there is on the seafloor, and there's very, very little uranium in whatever measurements we had in the mantle. Why is this? Why is there a disproportion there? So the young Earth creationists will say, we suspect that uranium was through a transmutation process on the continental crust related to Noah's flood. Have you heard that one before, Jordan?
Yeah,
From young Earth?
I've heard it. I'm extremely skeptical of that. That's usually in reference to the hydroplate theory.
Yes, yes.
That's how I hear it. And for those who aren't familiar, basically the hydroplates, the big plates of rock and stuff are vibrating or, moving around during the flood, the catastrophe. And that's leading, usually the way I hear it is leading to like static electrical discharge, and that high energy is causing fusion, and that's how we get the heavy elements. That doesn't make a lot of sense to me as the source of heavy elements for a lot of reasons. One of the easiest reasons is like it's not like uranium only exists on Earth. Like we can look at distant stars many light years away and they have uranium in them. So like, I mean, that came from somewhere, right? Like the hydroplates on Earth didn't throw uranium into a star a million light years away. So
yeah. Oh, Jordan, I don't mean to be rude, but sometimes when you talk, it gives me a chance to fiddle with the buttons and get my next screen off. So I'm trying to listen intently and multitask. But I did want to give the citation here, and unfortunately they didn't give. It's kind of hard to track down what peer-reviewed paper this came from. So this looks like this is the World Nuclear Organization. So they seem like a uranium mining type operation. This is not from a young Earth website.
I'm not a geologist, so I'm not an expert in like the processes that enrich the crust versus elsewhere, but I've read the same thing.
Okay, so then, oh my goodness, I have so many windows open I can't find what I'm trying to find, and so if you'll forbear with me here,
sure.
My apologies to you.
While you're doing that, there was a question that stuck out to me.
No, go ahead.
Dustin Buck said, correct me if I'm wrong, but uranium is the fuel. Palladium excites neutrons. ENT rubidium slows it down. I'm not exactly sure what that question is trying to ask. So I'm going to interpret it into a question that I would like to answer, which is how uranium fuel works in a reactor. So if that's not your question, you'll have to rephrase it. Basically, a nuclear reactor, a uranium-fueled nuclear reactor, the way most reactors work, they're light water reactors. And so you've got your fissile material, that's the uranium. And if we can get that to absorb a neutron, it'll break into two pieces and emit a bunch of energy. And it can do it if the neutrons are zipping around super fast, but it does it more easily if the neutrons are slower. And we call that moderating them. And so if you use a moderator, which water is the typical moderator, graphite would also work. The neutron bounces around in the moderator, it gets slowed down, and then those slow, which are called thermal neutrons for no good reason, are there is a good reason, but they're slow neutrons. They get absorbed in the fuel, and that's what causes fission. I don't know if that is at all what you were asking, but there you go.
Okay, I found this from the World Nuclear. Thank you for that answer, and I concur.
Good, because that's definitely
not that my opinion counts for much. Okay, guys, just a qualifier here. So the World Nuclear Organization says, it says here, kind of in the middle paragraph, the present-day abundance of uranium in the quote-unquote depleted mantle exposed on the ocean floor is about 0.004 parts per million. The continental crust, on the other hand, is relatively enriched in uranium at some 1.4 parts per million. This represents a 70-fold enrichment compared with the primitive mantle. In fact, the uranium lost from the depleted oceanic mantle is mostly sequestered in the continental crust. And so this has actually caused some problems for like people trying to do planetary, trying to solve the problem of planetary origins and how we get all the chemicals and the distribution, because the sentiment is, if it came from the stars and it was part of the original nebula, it would be throughout the whole Earth. But this distribution suggests that it was kind of a late raining down of uranium from somewhere. And
either that, or there's some kind of geological or chemical process that selectively
correct.
raises it up.
Correct. So I'm not going to, at this point, I'm not going to minimize that, because I have, there's just a lot of things we don't know. And by the way,
things I don't know.
Yeah. See, that's the thing. When I deal with someone who has actually gone through a curriculum, they tend to be a lot more humble, because it's like you think you know until you start to go through these classes, and then
like
you get hammered and you're like, ugh.
I do hold a degree in nuclear engineering. I do not consider myself an expert in nuclear engineering. I am an initiate. I know more than your like guy walking down the street, but like my professors and the guys who've been working in the field for decades know so much more than me. Like there's so much I don't even know how much I don't know,
Yeah. So we come, and what I've said is, you'll see in these a lot of internet places are just for theater and trying to make the other guy look bad. It's not about getting down to facts and having, real scholarly discussions. And I'm not, I debate rarely just for advertisement, but I said there's no reason to be debate. The reason debates happen is there's uncertainty about something. Things that we're certain of, you don't usually have debates over. Like a lot of the accepted theorems of math, you don't see people arguing about that. The only area in physics that is somewhat basic, where there's still arguments among professors that I hear, is about the concept of entropy. Everyone has their version of what it is, and it's almost laughable. I'll see professionals just kind of, it's like we can measure it, but they'll have a different description and they'll insist theirs is the right one.
In thermodynamics, our professor, Professor McCluskey, is great. Somebody asked him, like, well, what is entropy? He said, great question. Anyway, here's how you calculate it. Like,
right? Yeah. No, because it's an abstract quantity. Like length and mass, you have experience with it, and even temperature. You have a sense of what temperature is. Temperature is related to entropy, but entropy by itself, I'm just like, okay, S equals KB times the natural log of omega. I'm just like, that's it.
There's definitions, like it's the number of ways that you can arrange the microstates such that it doesn't affect the macro state. That's one way of describing entropy. There's like different ways of describing entropy. There's certainly ways that are wrong, like just saying, oh, it's just disorder. I mean,
that's very wrong.
Yeah, that's not.
And it's bad. It was by the founder, Boltzmann. He used that in a passing remark, and it stuck to this day. And Gibbs didn't help by saying mix-upness, and I'm just like, okay.
Yeah.
But where I was headed, the reason I threw that on the table was, there's no need to have arguments and make it, heated among scholars. If we don't know something, we'll say, okay, what will decide the argument? What experiment or observation and what result would settle this? That's the responsible thing to do. And
yeah,
the evidence. Just no point in just trying to just, but I said more debates doesn't solve the problem. More data will.
Yeah, data and models that make predictions that are falsifiable, that then are not falsified. That's how it's done.
So that being said, and this is actually also where, just so some people know that there was kind of a point to this, even though we may not get there anytime soon, is the young Earth creationists have postulated their model. One of the young Earth creationists, Walter Brown, has postulated that there was a nuclear transmutation event that involved large amounts of electricity, and that created the uranium concentrations on the continental crust. Okay, that can be explored. There could be experiments. There could be observations that'll confirm or refute that. And
I mean, just off the top of my head, we can cause those kind of electrical surges in the lab, right? And we could potentially, just spitballing, I'm not a scientist, you could potentially see what kind of isotropic composition you'd get from that kind of thing. And does that match what we find? I suspect it wouldn't, but
well, that's what is claimed. And okay, so you suspect it wouldn't. I would be skeptical also. The Walter Brown reports that Proton 21 lab, sadly in Ukraine, has, depending on what the target was of the electrical hit, will generate the isotopic distributions of uranium of interest, which that really caught my attention. I've since actually tried to get their books, their publications. They're mostly written in English, but there were piles of it. I actually thought about getting a PhD at Illinois Urbana-Champaign because that was the one university that was favorable to this electrical work. So that being said, I have this. Let me see. Okay, this is a Nature article that was published, but I have the archived version of it, and I'm just going to read the abstract.
okay.
And it relates to lightning. It doesn't talk about the isotopic distributions, but since you're a nuclear geek, you might find it interesting. I mean, just for itself, not immediately relevant to YEC, but it is leading kind of toward where Brown wants to go. But I'll just read the abstract for its own merits here. And it said this isn't the journal Nature, but you can get it outside of the paywall through the archive. Okay, so photonuclear reactions. Probably. I'm sorry.
Or through Sci-Hub if people aren't familiar with that. It's like Pirate Bay for peer review journals.
Oh, I didn't know there was a Sci-Hub. Thank you.
Yeah, I'll drop the link in the chat. Well, I don't know if I probably can't because I don't have a hammer, but I'll give you the link and you can do it.
I'm going to give you a hammer. Let me see if I.
Or wrench, I guess it is in YouTube.
Okay, hang on. Can you type something in the chat and then that way I don't have to search reasons to doubt. All right. You know, hide user and make moderator are right next to each other. It's so easy to press the wrong thing. And I've had some bots. I almost ended up making them moderators. And I almost accidentally hid you from the channel. Funny. I'm sorry. It would have been hard to undo that. But anyway, so thank you for dropping that in the side chat. Photonuclear reactions. This is 2017. Photonuclear reactions and lightning discovered from detection of positrons and neutrons. A positron is an antimatter particle, correct? Positrons.
Yeah, it's the antimatter particle of a electron. Yeah, the positively charged version.
Lightning and thundercloud are the most dramatic natural particle accelerators on Earth. Relativistic electrons accelerated by electric fields therein emit Bremsstrahlung gamma rays, which have been detected at ground observations by airborne detectors and as terrestrial gamma ray flashes, TGFs, from space. The energy of the gamma rays is sufficiently high to potentially invoke atmospheric photonuclear reactions. That'd be nitrogen 14 gamma and neutron, and then nitrogen 13, which would produce neutrons and eventually positrons via beta plus decay of generated unstable radioactive isotopes especially nitrogen-13. However, no clear observational evidence for the reaction has been reported to date. Here we report the first detection of neutron and positron signals from lightning with a ground observation. During a thunderstorm on 6th of February 2017 in Japan, a TGF-like intense flash, less than 1 millisecond, was detected at our monitoring sites 0.5 to 1.7 kilometers from the lightning. The subsequent initial burst quickly subsided with an exponential decay constant of 40 to 60 milliseconds, followed by a prolonged line emission at 0.55 mega electron volts, lasting for a minute. The observed decay timescale and spectral cutoff at 10 mega electron volts of the initial emission are well explained with de-excitation gamma rays from the nuclei excited by neutron capture. The center energy of the prolonged line emission corresponds to the electron-positron annihilation, and hence is conclusive indication of positrons produced after the lightning. Our detection of neutrons and positrons is unequivocal evidence that natural lightning triggers photonuclear reactions. No other natural event on Earth is known to trigger photonuclear reactions. This discovery places lightning as only the second known natural channel on Earth after atmospheric cosmic ray interaction, in which isotopes such as C13, C14, and nitrogen-15 are produced.
Neat.
Yeah, I mean, just outside of the creation evolution discussion, I just thought this was just so cool.
I noticed, so there was one thing in there that you pointed out. It was going from nitrogen 14 to nitrogen 13 by emitting a gamma ray and a neutron. And I thought, I don't know if people in the chat are familiar with how radioactive decay works, but I thought if it's okay, I might take a couple minutes to kind of like explain this, because I think this is something that's very commonly misunderstood. So the way radioactive decay happens is you have some isotopes in nature that are unstable. And there's very deep physics reasons for why they're unstable, but for all of us chickens here, you can just kind of think of it as there's not enough neutrons in the nucleus to keep the protons separated far enough, and they, for stability. And so at the low end of the number of neutrons, or the low end of the number of protons, you need about 1 neutron per proton. As you get to higher and higher protons, you need more and more neutrons. So eventually it's just unstable no matter what you do. Okay.
Can I ask, do the neutrons kind of help provide a little bit of glue, so to speak? Is that too simplistic?
You can think of it that way. Yeah.
Okay.
I'm sure.
Don't take that literally, guys. Okay. Don't take that literally.
I'm sure Leophilius is tearing out his hair as I butcher physics, but just for a basic understanding, you can think of it like the neutrons are like refereeing between the protons. They're not actually, but just conceptually, you can kind of get that way. So, anyway, so you need enough referees to keep it stable, and eventually there's just too many protons, and it just can't be stable no matter what you do, right? And so the atoms are going to try to get to stability by decaying through some method. They're going to emit something and then change it to something else that's moving towards the path. And eventually that will keep going over and over and over again until they get to stability, right? So there are a lot of different ways they can decay. The biggest ones are beta decay, which is just an electron. So it emits an electron, and if you look at the here's what I have, here's what I emitted, here's what I'm left over, all of the pieces should be conserved, right? So you should have charge should be conserved. So if you emit an electron, that's a negative charge, positive. You have to have a positive charge at the other end in order for those to cancel out. So you have a net, because the charge can't change. Charge is conserved. You also have to have the same number of nucleons being protons or neutrons, because mass is also conserved, like we talked before. And so that's why when you have something like that nitrogen 14, what that's telling you is nitrogen has some number of protons that I don't memorize. 7. Nitrogen has 7 protons. Every nitrogen everywhere has 7 protons because an element is defined by the number of protons it has. And the other number, that 14, that's the total number of nucleons, right? And so it has 7 protons. That means the other 7 have to be neutrons. Now, you can also have a nitrogen, like the one at the end, that has 13 nucleons. And so it also has 7 protons. It just has 1 fewer neutron, and that's an isotope. So elements, number of neutrons, elements number of protons, isotopes number of neutrons. Okay.
Oh, no, I think isotopes number of nucleons.
Well, yes, but that is correct. However, because the number of protons for any element is the same by definition, the number of neutrons is what will differentiate the same element to different isotopes.
Correct.
So, yeah.
But the number like 13 or 14 is
That's the number of
nucleon count.
nucleons. Yes.
Okay.
So the
Okay.
Z number is the number of protons. Every neutron everywhere, every nitrogen atom everywhere has 7 protons by definition. A nitrogen 14 atom has 14 nucleons, so 7 protons and 7 neutrons. A nitrogen 13, a different isotope, has 7 protons and 6 neutrons for a total of 13 nucleons. And so you see it emitted a gamma ray. Gamma is energy, which, you have some mass conversion, but don't worry about that. That's not to the level where we need to conserve it, so don't just ignore that. It emitted some energy in the form of a gamma ray and a neutron. A neutron is neutral, so the charge won't change. That's why it's still a nitrogen atom at the end, but the number of nucleons will change. You don't need to memorize all that. The important thing is radiation means it is emitting some kind of particle into the universe and then turning into something else at the other end. That's what radiation is. So it's not this kind of mystical field. A lot of people have this kind of like idea like it's a miasma or whatever. It's just particles, stuff that is being thrown out of the atom into the universe, roughly in a sphere around the thing. That's what radiation is. And to answer Dustin's question, he asked, radiation can cause cancer from what process? So radiation is dangerous because it has energy and also an electric charge. And so the way it causes cancer is particularly when a cell is splitting, when mitosis, right? When a cell's going through mitosis, I think that's what it is. My kids are going through like biology in middle school. That's the only reason I remember that term. When it's splitting, let's say it's a neutron. Neutrons coming in, it is like a bowling ball and will literally crash into stuff and mess things up inside the cell. Like that's literally doing physical damage to your cells. Alpha particles, which are a helium nucleus that's positively charged, has no electrons, or a beta particle, which is an electron. Those do the same thing, except they do it because they're electrically charged. But basically, the way radiation causes cancer is by damaging your DNA in the cell. So that's your 1 minute primer, 2 minute primer on what radiation is and how it works.
Thank you very much. While you're answering that question, I was busily typing, trying to find out the isotopes of nitrogen. Nitrogen 14 is stable. Nitrogen 13 is actually radioactive. It has a half-life of 10 minutes. I don't know what its daughter product is.
So, that you could actually figure that out if you went to the chart of the nuclides. You can just Google that,
Okay.
and the chart of the nuclides has every isotope that we're aware of in a big old chart. And I can actually share my screen, or you could share your screen.
Oh yeah, you can share it. I'd rather you walk us through it.
All right,
that'd be better. So I think, let me see. I can cut that one on. Hang on. So nitrogen 13.
Hold on, I lost my. There it is. Okay, can you see the chart now?
Yes.
Okay, so this chart of the nuclides, you can type in any nuclide you want, and you'll get all the information for it. So we'll do nitrogen 13, 13N there. Hit enter. It'll show you where it is on this little chart. And then down here, You can see a bunch of information. Most of it you don't care about, but this is nitrogen-13. The things you're going to want to care about are this right here. It's decay mode. That's the way it's decaying. In this case, it's electron capture with beta plus emission, so it's emitting a positron. And the half-life, which is right here. So 597 seconds for the half-life. And so what you could do is you just literally write down N13 plus electron with a positive charge. So, and then on the other side, what would that have to mean in order to conserve your charge and your mass? So putting me on the spot, that would, if it electron captures, that would turn a proton into a neutron because positive plus negative. So its product would be 13 with 6. Z number would be 6 because it lost 1.
Carbon 13, I think.
Yeah, so 6. Yeah, there you go. Cool, I didn't mess it up. And then we stopped.
No, don't trust me, guys.
Yeah.
It could be bad. Both of us messed that one up.
Okay, yeah. So that's how you could do it. You have so electron capture is a method where an electron falls into the nucleus. It doesn't actually, again, but you can think of it that way. Electron's doing its happy thing and boom, gets captured by the nucleus. A proton absorbs that charge and becomes a neutron because they're the same charge, right? And so the same number of nucleons, 13, but one fewer proton, was 7, now 6. An atom with 6 protons is carbon 13.
I would actually have to study what you just said carefully. So because you're doing all the conservation of charge or whatever, I'm just like, yeah, you know,
just
I'm being dyslexic. I can mess that up so easily.
Just the things you need to conserve are charge and mass. If you conserve those two things, then your formula will be okay. Now you're also going to be emitting like photons and some neutrinos and a bunch of other stuff. But if you're just trying to figure out if X decays with this, what's going to be left over? What's the atom? Then you don't need to worry about the neutrinos and gamma rays and all that other stuff.
So just kind of making it even easier for me, if there's a positron emission, a proton has become a neutron. Is that safe to say?
If charge is being conserved, if it didn't capture anything, yeah.
Okay, if it didn't capture, if it's just an emission, if it's just a positron emission, a proton becomes a proton had to become a neutron.
I'm very hesitant to say these broad sweeping things without
that. All right.
Yes. Leophilius wants me to say that spin is conserved too. Yeah, but we don't need to worry about spin if we're just trying to figure out what the parent and daughters are. So there's a lot of things that are conserved too, but for the purpose of figuring out parents and daughters, you don't need to worry about any of them. So engineering, for those who don't know, is the art of knowing what you can ignore. So we are ignoring spin.
Okay, so I'm just going to go by the assumption then if you have a negative.
I'd have to write it down in order to tell you. I should remember that off the top of my head, but I don't.
But I would guess. I mean, I'm just because this is a chance to learn, guys, and so just take it for what it's worth. And if people in the comment section later want to butcher, want to attack us for saying you got that wrong, that's fine. So my understanding then is if the nucleus releases an electron and nothing was added to it, that would mean the neutron became a proton.
Yeah, exactly, because charge has to be conserved, right?
So that's how I got the other one too.
I'm feeling more confident. I'm probably messed it up.
I'm feeling better now too, and I learned something. Okay, can you believe I went through graduate school and they didn't teach me that? We were studying classical mechanics, we were studying quantum mechanics, we were studying general relativity, something like that. Just no, that's not what I learnned.
So there you go. And
so this is very just for the viewers' benefit, you could see why young Earth creationists would be interested in this, where lightning can strike and it can actually create a radioactive isotope.
So
it's a transmutation from a stable isotope to a radioactive one.
Well, yeah. So so that right there is very similar to what would be happening in the atmosphere. The way that nitrogen carbon-14 is produced because it gets excited, and then that excited atom decays by electron capture, I think.
And actually, this paper suggested this is another source of carbon-14.
Right. And
So
so that actually reveals something important, that there's almost two classes of radioactive decay pathways. You've kind of got beta decay, decays that happen, or like special electron capture, but decays that happen because of electron interactions, and everything else. Because the things that happen due to electron interactions are to some extent they're vulnerable to the environment. Now that extent varies by the thing, and it's usually very small, but you can have environmental conditions affect those decay pathways because it has to do with the electron, and the electron is what mediates between the nucleus and the environment, right? But alpha decay and things like that happens purely in the nucleus, which is insulated from the environment, right? So
okay, dumb question. It seems to me, okay, I'm not going to ask for a sweeping generalization. I just say kind of a rule of thumb. It would seem to me that we don't have gamma emissions unless you're having also some sort of particle action going on, like say fission or just
outside of like cosmic rays, you can get gamma rays from just like the cosmos, right? But
right, but coming from a nucleus,
yeah, it wouldn't
won't
just. I mean, you could have a decay. It could decay by emitting a gamma ray that could be a product of decay, right? So some decay processes would release a high energy photon, an X-ray, a gamma ray, whatever. But it can't just get rid of a photon and like literally nothing else happen, because that photon has energy, right? And that energy has to come from somewhere, so.
Okay, that was where I was headed. I don't know of any. I don't recall any instance where the nucleus just shot off a gamma ray and it didn't change the nucleus.
So X-ray emission happens often when electron changes its orbital. So when electron drops from a higher energy orbital to a lower energy one, it does so by emitting a photon. And right. And so that's usually not as high energy as a gamma ray, but I suppose it could be.
Yeah, but that's not a nuclear process.
That is not a nuclear process, right?
Okay, all right. No, this is just good to. Okay, this is why we're having this discussion, so I could just get a handle on the basics.
So all that's sorry.
Go on.
Just finish the thought there. Many, many, many times when I talk to particularly young Earth creationists who want to point to a result where, look, in the lab, they changed the decay rate of beryllium-7, or they changed this decay rate from so many millions of years to 20 minutes or whatever it was. That is just about all. I don't think I've ever seen anything other than a beta decay, usually electron capture. And then, so you can't just take that and just generalize it everywhere.
Right, you couldn't generalize that to alpha decay. Okay, this is refreshing a lot of my memory.
They're two different things.
Yes.
I mean, if you think about it, electron capture requires that you capture an electron, right? The electron has to fall into the atom, and that's how it works, right? It falls in the nucleus, rather. Well, if you superheated it to a plasma and stripped all of the electrons, it would be stable. It couldn't decay by electron capture because there's no electrons to capture, So, like, in the extreme case, you could definitely affect it dramatically by just stripping it of all electrons. So, yeah, but that wouldn't do anything to your alpha decays, probably.
Yeah. So just to someone asked about the heat problem in hydroplate. I think we have to really work through their model difficulties all over the place, whatever model is adopted. So we're not there yet. Okay, guys. So that's why we're having this discussion. And as I said, I announced that I'm thinking about moving out of biology back into physics. because that was really my first love. I'm glad I had the opportunity to participate in the biology discussion, and I do feel that I was able to contribute. But where I think young Earth creationism is needing some more researchers is in the areas of like what we're talking about tonight. So with just for those who are not aware of hydroplate theory, obviously the atmospheric lightning is not going to be, I mean, just as a superficial guess, it's not going to be enough to create all the uranium that's on the continental crust.
No, for sure not.
So the theory is that there's a piezoelectric effect. When there are tectonic activities, it can generate huge amounts of electricity. There are pictures of during earthquakes, lightning being generated, which they believe coming from the earthquake source. So like your butane lighters, supposedly that uses the piezoelectric effect where you're compressing the quartz or doing something or banging the quartz together, it makes an electric spark. You can imagine that happening on continental scales. It would generate a lot of electricity, cause a lot of lightning. I don't know if you would have these electrical discharges into the ground, which is be very important for generating all these elements. So just showing where some of this was leading, but really my purpose tonight is not to prove the theory. It's just to see, just to lay out where some of the young Earth creationists have put this on the table. And I'm just in the process of just spooling up and learning the nuclear physics. I think for all parties involved, because the Earth system is so gigantic, it's not like we can do this in a test tube and say this is the way it's done, because when you deal with the Earth system, you're dealing with so many variables, and we're also trying to postulate what the Earth was like long ago before it's in its current configuration. So there's going to be a lot of unknowns,
Yes,
that's why I liked biology for a while, because it was at least confined to the test tube. You could argue over how things happened if it's right there in the test tube.
But events that happen even in the distant past will leave fingerprints today, things that we can see. One of my favorite examples of that, Dustin Buck, X-rays are considered radiation. Yes, they're radiation because it radiates from the atom. That's radiation. Anyway, one of my favorite examples of that is the Oklo phenomena, which is just the coolest thing to have ever happened ever. Are you familiar with the Oklo phenomena?
Oh yeah.
Yeah. I don't want to derail the whole thing, so I'd happily go into it if you want me to, but just the very brief.
Well, yeah. You know what? Why don't you touch on it and we could explore it later, because I could tell it's something you really want to talk about.
It's just
we want to have fun here tonight, okay? We're gonna have fun. So
we'll very brief, just you can Google it. Oklo was a naturally occurring nuclear reactor. A nuclear reactor that occurred with no human intervention in the ground in nature. It's amazing. And because of Oklo, we have like a kind of benchmark that we can we know that fission happened in the past because of the isotopic configuration, the amounts of all the daughters we see. You only get those comparative amounts of daughter elements from fission. You wouldn't get it from other decay pathways, and so that's how we can know. Like, even though it would have happened very, very long ago, there's clear evidence.
And I'm sorry to throw a cold water on your enthusiasm. Some young Earth creationists have a different interpretation of the how Oklo worked, and I happen to know of another nuclear engineer who he's also fascinated by it. So that's all I'll say. I'm not saying you're wrong. I don't know. Okay, so and it was Walter Brown who examined this. So all right, guys. So let's see. We're already at an hour and a half. We had a lot of fun. And I think the Oklo thing is something to hold out if we have another talk. So let me just if you had, why don't you talk more about it if you want, because I need to go look at my docket here to see if there are other things I was supposed to talk about.
You made a mistake. You let me talk about nuclear power. So okay. So, in order to have nuclear power work, in order to get sustained uranium fission, what happens is the uranium atom, U-235, the fissile stuff, it splits apart, right? Because it absorbed a neutron. And when it splits apart, it emits 2 and sometimes 3 neutrons. So you got more neutrons out than you put in, right? And so those neutrons then go out and get absorbed by new uranium, which then they spit out more, and that's how you get a chain reaction. Okay, that only works in the presence of water. Well, I mean, it can work in a fast reactor, but not going to get into that. You need a moderator, you need water in order for that to work. I talked about that a little bit earlier. You also need to have your uranium enriched to at least 3%. A little bit higher is better. And that's because most of your uranium is not fissile. If it absorbs a neutron, it will not fission. So you need about 3% of it to be that fissile stuff. Okay. In nature right now, our uranium is 0.7% enriched, but the U-235, the fissile stuff, decays faster than the fertile stuff, U-238. And so in the future, it'll be less enriched, meaning in the past, it was more enriched. If you go back 2 billion years or so, you can do the math, it's about 1.8, but 2 billion years, the natural uranium in the ground was about 3% enriched. So if you get uranium, this 3% enriched uranium in the presence of water, you're going to get fission because uranium spontaneously fissions with some frequency. And as soon as one spontaneously fissions, you get a chain reaction. And this was theorized several years before it was found. And they found evidence of this at Oklo. They found depleted uranium in the ground, uranium that had underwent fission. So the fissile stuff had split apart. There wasn't as much of it anymore. And they also found all of the fingerprints of fission in terms of the fission products. So really cool, a naturally occurring nuclear reactor in the ground. And it also shows that capturing radioactive waste or the products of fission in a geologic area is feasible because these fission products are literally right there and they've been there, by our view, 2 billion years, so that's Oklo in as brief as I can possibly make it.
Oh, that was actually, thank you, because it is, I'll tell you the value of that. It's good to get kind of the secular perspective, because sometimes when you read it from a creation perspective, you don't know what's being filtered out. So this was actually refreshing to hear it from this first time I actually heard it from the secular perspective. Again, sometimes I'm reading through these creation materials and I just did not have time to delve into some things. We get stuck in our specialty,
Yeah,
unfortunately, and I skipped over the Oklo stuff. But I think it'd be nice to investigate it more and then also study the topic of fission. So now I'm going to go into kind of just some strange territory here, because again, it could be a fishing expedition, whether we get anything of benefit for the young Earth creation community. But since you're interested in nuclear stuff, and I am, especially today, we'll just run through some of it. So
okay.
I'm not endorsing this, but there's one thing you already mentioned. We don't need to cover it more. Let's see, get this up and going here. Do nuclear decay rates depend on temperature? And since you said about the electron stuff, I think that we can find cases. I've seen it even on Wikipedia where pressure and temperature can affect the decay rate very, very, very slightly. Not anything near the accelerated nuclear decays that young Earth creationists want. So
and the temperatures and pressures involved are immense. But yeah.
Yeah. So I'm just trying to tie up a loose end. So I'm going to just kill that window. Now, the interesting thing here, there was a very scandalous meeting at the American Chemical Society. So there are two big societies, scientific societies in the United States. The American Physical Society, which are physicists, the American Chemical Society, which are chemists. In 2012, they had a meeting that focused on cold fusion. All right, the reason it happened was they could see that there were respected chemists who are working on these projects, and also a government-funded project at the Naval Space War. It's called SPAWAR. It's the Space Warfare Unit that was exploring this. So whether we agree or not, we had at least enough respected people that it's like, okay, we're going to give them an audience here at the American Chemical Society. It was scandalous, but I'm just, this is continuing, and I'll give some of my opinions. So at first, I'll just read what was there. This researcher here is Vladimir Vyastovsky. He is head of the Department of Mathematics and Theoretical Radiophysics at the Taras Shevchenko National University of Kiev, Ukraine. And this is kind of sad because one of the co-authors with him on this paper is from Moscow. So it is nice to see them collaborating, and I'm, I feel for what's going on there, that relationships are being, livelihoods and relationships are being strained because of what's going on. But he presented a paper, and it's called here, Transmutation of Stable Isotopes and Deactivation of Radioactive Waste in Growing Biological Systems. So what, okay, I know some of you guys will just roll your eyes. He's very interested in remediating the waste at Chernobyl. And there is much rejected work by Kurvan, who claimed that he could get transmutation in biological organisms. And so this happened at Chernobyl, and as far as I could tell, they were successful in remediating using biological bacteria. And so, again, it depends on the decay pathway that's involved, and they may not actually know the mechanism. All right, so just take it for what it's worth. I think it'll be more believable. One, if we can continue to replicate the experiments, there's no interest here in the United States because that's just considered crank. But I will tell you one thing that I do know about biology. Biology is very good at controlling subatomic particles. The ATP synthase enzyme, they can push an individual proton across a canal. I mean, that's pretty impressive. When you can control subatomic particles, their direction and their flow and their position, I think that's impressive. So it would not totally surprise me. There may be situations you can, biology could exploit that. So just suffice to say, no need to argue over it. The way to settle it is more observations and experiments. Right. Anyone's able to replicate it, I'm all for it. I just need to throw that out there. He's obviously a respected researcher. He would not have arisen to that stature if he didn't have some brains, and he certainly wouldn't have been invited to the American Chemical Society if he weren't respected.
Right. I did read that paper because I hadn't seen it before. It's interesting. I'm not a biologist, so I mean, if we could have some kind of microbe that could speed up the decay of common fission products, that would be of extreme interest in the nuclear community, because we're always looking for better ways to dispose of spent fuel, and the less spent, the fewer radioactive products we have to take care of, the better. Like, that would be amazing. I haven't seen anyone reproduce it anywhere, and the paper was in 2013, but I mean, who knows? I did go through it, and I noticed one error which doesn't imbue me with a ton of confidence, because it's a pretty basic error. They at one point they're talking about transmuting barium 140 by combining it with carbon 12, and that yields I think it was samarium 152, and they said the reactions are energy favorable and the energy of the reaction is positive, and they listed at 8.5 megaelectron volts, which immediately set off my alarms, because barium is heavier than iron, and typically if it's heavier than iron, fusion, this is fusion, is endothermic. It takes more energy than it gives off, right? And the reason for that is the binding energy per nucleon curve. And so I touched on this earlier. Yeah. So generally speaking, heavier than iron. If you fission, then it's then you have a net positive energy, and lighter than iron. If you fusion, you have a net positive energy. So I
Well,
did the. Sorry, go ahead.
I just want to say I want to thank you for that.
Yeah.
Oh,
So
go on.
if
I can't, I can't thank you enough that you would actually go through that paper, and your eye would pick that up.
so
That's valuable.
So
This is,
it's
guys,
like,
this is worth gold. This is why this conversation, Jordan
I
has
mean,
made this conversation worth it just for that, and plus even some of the other things too. So thank you.
the good news is the math is very simple. It's like literally freshman level math. So what you can do to test this is you can just look at the masses of the atoms involved. You can look up the atomic mass of barium 140. You can look up the atomic mass of carbon 12, which is 12 because by definition it's 12. Fun fact. And you can look up the mass of the samarium 152. And then you say, okay, the mass of the inputs, add those together. The mass of the outputs, add those together. Subtract the two. And it turns out that the outputs have more mass than the inputs. Okay. That mass didn't just come from nowhere. It has to come from something. And so what that means is that the reaction is endothermic. It requires energy input. And it turns out it actually, you have to do the equation I just told you, then multiply it by 931.5, 931.5, because that's the conversion between mega electron volts, which is a form of a unit of energy, and AMUs. So do that. I just told you, massive inputs minus massive outputs times 931.5. That'll give you a number of mega electron volts for your energy. And it's negative 8.5. So actually, this reaction is not positive, it's negative. So it requires 8.5 mega electron volts to happen. So they flip the sign. Also, on the next page, they do a very similar equation with cesium. Cesium 137 plus a proton equals barium 138 and some energy. They said it was 5.58 mega electron volts. I got a positive number that time, same as them, but I got 9 mega electron volts. I ran it like 2 different ways. I compared the binding energies. I compared the masses. I was like, this is very simple stuff. And this is a peer-reviewed paper. And I'm like, I must be wrong because there's no way this got through peer review with this kind of error. But and maybe I am wrong. Please tell me if I am. But it seems wrong. And so I don't.
Let me just say, my inclination is to say that there's some slop on their writing. Okay.
So maybe
I think
maybe they wrote it down wrong. Maybe there's pieces in there that they didn't articulate. So like there's more to the situation than they just described in the paper. I don't know.
But it's sloppy work. As far as we can tell, it's sloppy work.
Yeah.
And the reason I'm backing you on that, I saw one of his presentations. It had errors in it. And I'm just like, okay, there are some things that are because of the English barrier. Okay, I really sympathize with that. But
yeah, I would have forgiven.
I could tell you, having been a part of seeing how some peer-reviewed papers are written, I'm just like, yeah, you focus on the really big things, and sometimes really stupid stuff gets through there, especially well, they only have 2 authors, so that's not a good excuse. I've been on some with like 10 authors and just like, yeah, I'm not going to catch stuff that the other guys did. Just no way.
Right.
So
but the first one, at least, though, is a small thing. It's just a switch sign, but the implications are important because that means it's not energy favorable. It requires energy input. So that would completely change the whole nature of the reaction.
So let me just say this, okay, why am I throwing this out? I continue to be surprised what we're learning about how we can do nuclear engineering. And nuclear engineering, I always had a heart for renewable energy. And so that's why actually I got interested in this in the first place before even young Earth creationism. But some of the principles in nuclear engineering might give us insight into mechanisms of how nuclear structure could be changed naturally. which is what the young Earth creationists want. So I just want to say the difficulty for the young Earth creationists is for the origin of life, they'll invoke a miracle. For the emergence of all the diversity of life, invoke a miracle. When it comes to Noah's flood, they want as many naturalistic mechanisms as possible because it enables a historical reconstruction, and it's a little bit more believable. You know, the idea is if you can claim Noah's flood happened for the most part naturalistically, with maybe the exception of the ark. I think the ark would have to be a miracle. I think there's good arguments that it's kind of infeasible unless God were helping you along.
Yeah,
I'm perfectly, but for the rest of it, what makes this a particularly difficult thing is we're going to try to invoke naturalistic mechanisms so we can do a historical reconstruction. So to the extent we find alternative means of doing transmutations to account for the daughter products and then also the radioisotopes and then the proportions, that's the problem the young Earth creationists have to solve. So, you know, sometimes you just have to look in all sorts of places to see if there's a mechanism that might alleviate or give us insight.
yeah.
And I'm not saying that the problem is solved by any means, but this is guys, this is what a professional creationist researcher has to go through, not someone who just talks and does debates. This is really trying to solve model problems, and it's nightmarish and difficult.
I can say some
yeah.
young Earth creationists that I've spoken to have this idea that something like that would never get researched, not because it's not real, but because, you know, they don't want to know this kind of information. And say what you will about researchers, but I can guarantee you the nuclear industry doesn't care one iota how old the Earth is or anything. All they care about is whether they can make money by producing electricity. And
Yeah.
so this kind of research would help them make money. And so you better believe that if they thought it was real, they would fund it. Because, you know.
And I would agree with you, because we've actually seen it like with this whole junk DNA debate. The medical research community has actually been the friend of creationists. You know, there's kind of a little bit of a side battle on the junk DNA debate. And the creationists were just kind of applauding what was happening at the NIH because they're trying to solve cures for cancer. And so kind of the research was no longer suppressed because it had a benefit to society. And that's why I'm kind of interested in this with alternative energy, renewable, especially now with the push for renewable energy. I mean, you know, I don't get involved in the climate change debate that much, but I am a conservationist. You know, as the population grows, we need more physical space, or we could either somehow figure out how to reduce the population size, and we need to conserve the resources because they're finite.
Mm-hmm.
So I'm all on board with that. So I threw that out there, and that relates to something else. And I'm going to show a diagram here. See if I could bring it up. If you had some comments while I'm grabbing this, feel free. I liked what you said, by the way, just now. I concur. I concur with what you just said.
I completely agree when it comes to renewable energy. That's part of what makes me so passionate about my field and wanting to be involved in nuclear engineering, because we need clean ways of producing energy. Nuclear energy is one of those. Solar power is another. Wind power is another. But we don't have the luxury of not doing those, you know. So
yeah, exactly. And so I was interested in this a lot. And again, I need to say, okay, I had to be very careful when I made my presentation in 2012 at my solid state physics class, because I didn't want to use the term cold fusion. So I had to be very careful. Now, one reason I was glad we talked about these photonuclear reactions and so forth, I'm realizing anytime we have a transmutation of an element, we don't always have to invoke fusion or fission, and that helps. So one thing, the reason kind of quote unquote cold fusion, and I think it's a misnomer because we don't actually know what's going on, it has persisted, is we are getting strong evidence of nuclear transmutations, and people will say it's cold fusion, but we don't know what the mechanism. what the reaction mechanism is. So Mitsubishi Heavy Industries and Google are financing cold fusion research. And I just want to say, guys, time out. I think your heart's in the right place to get renewable energy, but what we may be seeing may not actually be an avenue toward an energy source, but it is an avenue toward changing nuclear structure. Whether we can make renewable energy out of it is another story. But where I'm headed with this is the reason I'm getting the sense that everyone is saying there's definitely been measured transmutation. And given what happened with the lightning strike and stuff, I'm just like, yeah, okay, I think that's a given now. If you could just prove that you transmuted elements, my barrier of accepting that is kind of low at this point. If you say it's fusion, I'm just like, that's kind of where I draw the line.
You can transmute elements without fusion. The one doesn't imply the other.
Right. And so I think there's a little bit too much eagerness to conflate it because they want to call it fusion and they're getting energy. Some theoreticians have said there may be ways you can actually do transmutation and get excess heat, and it's not fusion in the kind of the brute force that we see in the sun or our thermonuclear weapons.
I mean,
it might be some other mechanism.
Sure. At the end of the day, if your thing at the end, if the binding energy per nucleon is less, so you've got spare energy, that'll release energy, right? Like that's
Yeah,
it's just what's going to happen.
Yeah, so there have been a variety of theories thrown out, anywhere from saying we're going to amend the laws of physics, which I'm just like, nah, you don't tinker with that without a lot of headaches. You might be better off saying maybe a reinterpretation of our understanding, and there's been a lot of that. And then I think at this stage we just don't know. But I wanted to show this graph here. I mentioned the Mitsubishi Heavy Industries and Google throwing tens of millions of dollars at university professors. And they're willing to do that because these are like senior researchers that got their reputation in other chemistry. Meaning I'd be suspicious if the only way they made money was trying to do transmutation experiments and they weren't mainstream professors in mainstream universities. But this is starting to happen. And this is one of the transmutation reactions that they're claiming. And I don't know if I put it in the video description, Wamura, he's showing here, and I don't know what SM is. BA?
Barium is BA, SM is samarium, I think.
Yeah, that's what I would think too. So what they did, the classic thing that they like to use is group 10, especially palladium. It's a group 10 element in the periodic table. And they put deuterium and loaded into the palladium somehow. And then they mixed in this barium 138. And their proposed reaction mechanism is you have 6 deuterons.
Which, for those who don't know, deuteron is a hydrogen atom with a neutron.
Okay. Thank you. And they ended up getting a samarium 150. So the math looked good. And then they took a barium 137 isotope, and they got a 149 samarium. So that was the claim there. And they used how they're able to make these determinations as to what, whether you had trace elements or not. That's an experimental method. I'm not aware of how they do that. They use something called MOSBAR. Have you heard of that? MOSBAR?
I have heard of it as of like 3 hours ago because I was reading through a paper where they talked about it. It's a way of it's spectroscopy, but not your usual spectroscopy for stars. They basically shoot it with gamma rays, and certain energies of gamma rays are absorbed, and that tells them what's present. I think that's basically the gist.
Right. So the interest of these other kinds of reactions would be very important for understanding nuclear remediation, because you know, we have that really high-powered one that was the where they use photonuclear, and you're gonna have to be firing off a lot of gamma rays to make all these neutrons,
Mhm.
and to do it's going to be a painful remediation step. But it, you know, if they're able to elucidate the mechanism, that might help us understand if at all the bacteria are able to actually do what the Ukraine researcher said. It might give us insight how low energy nuclear reactions can
Yeah.
happen.
If they
And
can do it, awesome. That'd be great. I'm skeptical, but if they can do it, that'd be amazing.
yeah, so I'm skeptical too. So how does this fit into young Earth creationism? I think that for me, and even really people who aren't even young Earth creationists, we ought to be rooting for these guys to bring it mainstream. One thing I have heard, and I just heard this by probably the most respected researcher in these low energy reactions. He said, so much of this has happened by serendipity, the difficulty in recreating it. We found out that if the reactions, the reaction centers are in the cracks in our palladium. These were actually defects in the electrodes. And he said, we don't know why these accidental cracks are the reaction centers. With the implication is, if we knew how to actually make the crack so that it works, that's what we would do. So that's why there's been a lot of hit and miss. And he said, okay, so we have like 1% of the experiments do really, really well. And then, you know, the rest are kind of on the other side of the curve. They are able to get transmutations, but the thing they're really looking for is excess heat. And they know that they're going to have to do some sort of nano engineering to get the excess heat, so they could kind of replicate what's happening in the crack. That's where they are right now. But the thing that he said is no one really understands, no one can state a mechanism for why this works. So we can understand thermonuclear fusion. It's just very brute. You get high enough temperature, and I guess they're in close enough proximity, just brute force it.
Yep.
And we understand fission. The transmutation mechanism, okay, I'm just accepting, you know, at this point, even though I'm skeptical, that the transmutations were detected. Because if you have elements there that weren't there before, you know, I'm accepting that, and hopefully they're very good about controlling purity, etc. They have to figure out what's going on. So I would be excited, and I do think it would be relevant to young Earth creationism. So that's pretty much all I had. I think I learned an awful lot tonight, and I don't have anything else to add. So I was thinking we would have much more future shows. Maybe not on this. We might talk about like the carbon-14 and contamination. And you know, since I already agree with your heat assessment of the isotropic accelerated nuclear decay, you're not going to get any argument from me there.
I mean, I will talk about nuclear physics and nuclear energy to absolutely anyone for any reason. So
Okay, that's great.
you won't have to
That's
twist
great.
my arm very hard to do that.
All right. So I haven't been monitoring the chat. This is guys, if while Jordan and I are here, I'll, you know, another 5-10 minutes. Okay, Jordan?
Sure.
All right. If they have questions.
Scrolling through, I heard that most uranium was encased within the granitic crust. Yeah. Your granite countertops are radioactive. Most things are radioactive. Bananas, for instance. You live in a radioactive world, so. But it's okay, because a little bit of radiation isn't that big a deal.
Nuclear physicists, no, they help. They help with. Well, there's a lot of radioactive medicine, and there's nuclear energy, and
you
really,
can't go to space without nuclear reactors.
Yeah.
So.
And I think they will help us. My feeling is just understanding God's creation is always good. So let's
Yeah,
see.
I mean, when I was a creationist, I viewed the study of physics as a way to explore God's creation, right? So, if you do believe that a all-powerful deity made the universe, I mean, what's a great way to learn about a craftsman? You study their craft, right? So, I mean, nobody should have anything to fear from the truth. If what you believe is true, then more evidence is only ever going to support that. So, and if you're wrong, the only way you're ever going to find out is through evidence. And if you find out you're wrong, you can just change your mind, and then poof, like magic, you're not wrong anymore. So, you know, everyone should be on the same side when it comes to that.
Oh, Leo Phileas said this. Most of the mass of atoms has to do with the energy of the strong interactions. It's not the total sum of the elementary constituents.
Yeah. If you just like weighed the subatomic particles, if that was a sensible thing that could even be done, then yeah, it wouldn't, like, the mass wouldn't be the same as like the measured mass. But that's getting like super into the weeds,
Super into the weeds.
which you don't need to understand unless you're like a particle physicist. So
Did you, there's a lot of stuff with quarks, and I've never even touched that. Did you ever need that in your background for
no,
dealing with quarks? Okay,
we
so there's a part of nuclear physics you don't need to study quark theory, because some of the guys like Leo Phileas and others bring it up, just like, I never learned that.
I'm aware of their existence. We covered them as a thing in my modern physics class, but modern physics is like, it's a senior level class, but it's like senior undergrad, so like it's not like we talked about it. We talked about what they are and why they exist and like the different configurations, so like I'm aware of them, but to do nuclear engineering, to run a nuclear power plant, I never have to like quarks may as well not exist as far as I'm concerned. Like it just isn't relevant for that. So it's not like, it is a very important thing if you're going to do nuclear physics. Obviously, that's the nucleus, but if all you're interested in is like radioactive decay and stuff, you don't need to worry about it.
Magnets are very important to nuclear physics.
Sure. Magnets are super useful.
Yeah, and well, that a lot of the particle accelerators have these giant magnets, and for the young Earth creationists, we use accelerator mass spectrometry, which uses magnets to be able to separate the carbon-12 from the carbon-14
based on its mass number.
So yeah. So some of the nuclear physics, I've actually let me just say this, Mitchell. I'm praying God will send more nuclear physicists into the young Earth creation community. There's a shortage of them. There's a shortage of us that can understand general relativity. I took a class in it. I'm just like, when I went to a creationist conference, I think there were only 3 or 4 people, and I was one of them. I said, that's kind of scary because I knew squat. So they're not. We have an overabundance of preachers, not enough scientists. That's just my biases.
My modern physics class touched on relativity. We talked about special relativity a lot. We missed a class because of a snow day, and the professor was like, well, you guys probably won't need general relativity, and just like they kept on going.
It's an important theory to kind of patch up a lot of holes in our understanding, but a lot of everyday technology does not need it. Maybe the GPS satellite technology needs relativistic corrections.
Most you can ignore relativity in your everyday life. You're never going to need relativity. That there's a reason why it took hundreds of years to be invented, right? Probably, like you said, the closest thing that it comes to affecting you is your GPS satellites have to take it into account because time flows slower for them. So, otherwise the clocks would be out of sync.
So this is why I'm passionate about helping Christians and creationists through school. There's a shortage of us. There's always been, it's starting to alleviate now because I'm actually meeting a lot of creationist biologists at the PhD level, also chemists. They're slowly more and more physicists. The most well-known would be John Gideon Hartnett, he's an excellent secular physicist. And I'm going to close by reading John Hartnett's wiki entry. But Jordan, before that, if you had some thoughts you'd like to share while I dig this up, and then I'll just close with John Gideon Hartnett. And I really
Sure.
want to thank you again from the bottom of my heart that you spent time with me, and we'll go into maybe the radiocarbon dating discussion at some point.
Well, thanks
I
for
feel a little bit like you've kind of given me a refresher that I need to get into that discussion. And then there'll be other, I think the other stuff will be stuff that I'll have to learn. I'm not going to be going the route of saying, oh, this is unreliable. I really just want to understand the mechanics because each one has a different decay path.
Mhm.
And, oh, now I'm sorry. The one thing I did want to do is they've talked about the origins of the carbon-14 in fossils. Either could be contamination or outside sources of like radiation, neutron.
Yeah.
I would like to go through the calculations there. So that'll be definitely nerd torture. I'm not saying that we're going to get it right, but I'd at least like to give it a lot of people have been arguing contamination and then other, thorium and uranium. I think it's just the responsible thing. You seem like the sort of guy that would be willing to go through the numbers with me.
I mean,
or at least try. At least try.
If someone wants to throw out some numbers, I'd be happy to look at them.
Okay, so and it's only fair. I'm not going to put you on the spot to say is this right or wrong. I'm just going to say, okay, this is creationist theory. We'll talk about it here on the show, and then we can get back later. Because I need to kind of even like what I probably do is I'm going to bring a creationist paper and I say, can you help me read through this? Just like what we did with the two papers we had today. I could read it, but it was more beneficial when you were there beside me and we're reading it through together and saying, is this what the author, do you think that's what the author was trying to say? And, and we'll just go from there. So that might be the next show. And I don't know if John B will be able to join us. But if you had any closing thoughts while I get John Gideon Hartnett's bio up.
I'll just shill my podcast real quick.
Oh, yes. Let me put a note on my things to do. I need to put, you can put it in the side chat if you have a link to it.
I do.
And I'll try to put it in the video description.
Yeah, so my channel is Reason to Doubt. We're a podcast that also happens to post on YouTube sometimes. We're a podcast about skepticism. And so what we generally do is we examine claims from a skeptical viewpoint. So we do about half religious content and half non-religious content. So we do stuff like look at whether aliens have visited Earth or whether the Earth is flat, and also things having to do with nuclear power and things having to do with like theology, because I do it with my friend Jared, who is an atheist as well, but he has a degree in divinity, went to seminary. So
who's this?
My friend Jared, we knew each other in the Army, and we decided to do a podcast together. And so I'm like the science guy, and he has a degree from Liberty, I think, but he's an atheist. And so we basically are trying to further the cause of skepticism. And I'll just say that we don't view skepticism as opposed to religion necessarily. Skepticism is all about apportioning your belief in relation to the evidence, believing things for which you have evidence and not believing things you don't. And so if you have examined the evidence, like a gentleman we just interviewed, Jeff Swearink, with reasons to believe, he's an astrophysicist who is a Christian. And so if like him, if you've examined the evidence and weighed it reasonably and done your best, and you believe honestly that the evidence is that God exists, then congratulations, you are a religious skeptic. You know, that's all skepticism is. So I think there's something there for everybody, and we're always open to taking requests. So if you have something burning that's been happening you want us to tackle.
So Jared was he a Christian at one point?
He was, yes. So we were
And
both former Christians who are now atheists. When I met him, actually, he was a Christian who was going through seminary, and he realized just as he was about to graduate, like literally months before he graduated, that he could no longer hold on to his faith. So he deconverted as I knew
yeah.
him.
I mean, as I said, that I came from I was never an atheist. I did have some bouts of agnosticism, but I came from an evolutionary viewpoint, and I would just say this is where I am now. I think it's easier because I think that sometimes the stuff that they teach in church and the way they drill it into you, I think these poor guys are just ripe for getting deconverted. I think it's easier for someone to come from a secular environment and then become a Christian. He's more likely to hold on to it, is what I was trying to say. If you come from a secular environment, decide to become a Christian, it's just been my experience that they're more likely to hold on to it, because I meet a lot of ex-Christians, and I'm just like, yeah, I can kind of get where you are, you know, because it's a shock to find out that people have another viewpoint and it's so opposite your own, and they you know, so that's why I'm particularly interested in deconversion stories, because for myself, I nearly got deconverted. And I do have to say this, it was my experience, it was a big contributor was people in the church, actually. Not just the people outside. They did a very good job of, you know, making me almost leave. So thank you.
Well, if you want to hear it, you can listen to our deconversion story. It was one of our first episodes.
Yeah. Actually, I'm having I'm having a hard time copying the link, but I can do it later. I'll try to remember to put it in the video description. Yeah, I'm going to have to do that. I'm sorry.
No problem.
Unless I can, let me see. Let me just try one more time to see if I can get it on my other computer. Because to copy it off the StreamYard, I mean the Restream thing is kind of hard. So let me.
I can also just email you some links.
Oh, could you?
Yeah.
If you do that, then I'll put it in my video description. That's also a reminder. And I'm happy to advertise that site. There are some people and sites I don't advertise on this channel. So you're special, and I do look forward to us meeting again. So I'm gonna read John Gideon Hartnett, just for the young Earth creationists out there. He's a secular physicist, but he's also a young Earth creationist, and I think he's a very good role model for young Earth creationists who wish to go into the sciences. He invited me to be his PhD student in Australia, but I was taking care of my mom, and that was pretty much off the table just for that reason alone. Not to mention, I didn't like having to drive on the left side of the highway and sitting in the right driver's seat. I said, I'm dyslexic enough. I know I'm going to get in an accident trying to drive in Australia. I don't know how people are able to switch sides of the road and drive from the different feet. I couldn't do it, and that's kind of sad, because I would like to travel more and to be in places like that. So let me read about John Hartnett. John Hartnett is an Australian young Earth creationist and cosmologist. He's been active with Creation Ministries International and is known for his opposition to the Big Bang Theory and criticisms of dark matter and dark energy hypotheses. He received both his BS honors in 1973 and a PhD with distinction from the School of Physics, University of Western Australia. He currently works as a research fellow at University of Adelaide, South Australia. He's published more than 200 papers in scientific journals, book chapters, and conference proceedings, holds 1 patent, works on the development of ultra-stable cryo-cooled sapphire oscillators, and participated on a sapphire clock ensemble project, the Atomic Clock Ensemble in space mission run by the European Space Agency. He has also written articles for several creationist journals, and according to Creation Ministries International, Hartnett believes that God is the real creator of the universe, as the Bible says. His research interests include ultra-low noise radar and ultra-high stability cryogenic microwave oscillators, and clock based on pure single crystal sapphire resonators. Applications for the latter are to provide low noise local oscillators to atomic physics labs, time and frequency atomic fountain standards, and very high frequency VLBI, very long baseline interferometry, radio astronomy. The terrestrial clock technology co-developed by him is claimed to be the most stable in the universe, with Hartnett et al. Stating that it outperformed the stability signals generated by pulsars, rotating neutron stars that produce highly periodic bursts of radio waves, such as astronomical sources, are then used as natural clocks for tests of physics. Further, he is interested in the development of cryo-cooled CSO resonators, detection of WISPs using low noise microwave techniques, tests of the fundamental theories of physics, such as special and general relativity, measurement of drift in fundamental constants and their cosmological implications, and cosmology and the large-scale structure of the universe. So when you've been hearing, guys, the creationists out there, when you've heard me be critical of Kent Hovind, compare Kent Hovind to John Gideon Hartnett. If you want to be a creationist and you want to be a scientist, you want to be an example, you want to be like John Gideon Hartnett. You do not want to be like Kent Hovind. So I'm sorry to be preachy there, Jordan. I was glad to see you nod there.
I
with
agree.
approval.
Don't be like Kent Hovind for a variety of reasons.
Yes. So guys, thank you. It's been fun. And Jordan, heartfelt thanks for this. And I'll meet you backstage for just a few minutes, just some administrative things. Guys, take care. God bless you. Have a good evening.